Hello to all physics enthusiasts and fans of physical experiments. This is Andrei Shchetnikov with you, and we continue to make our videos on electrostatics. In today's video, we will discuss the concept of electric field flux and Gauss's theorem, which allows us to replace complex calculations based on Coulomb's law with much simpler ones. But I will start this discussion not with electrostatics itself, but with a useful hydraulic analogy. So I filled a syringe with water, connected a tube to it, and placed it inside an aquarium. And now I begin to inject water from the syringe. And it is clear that the amount of water entering the tube from the syringe is the same as the amount exiting from the lower end of the tube. Moreover, let's surround the lower end of the tube with an arbitrary closed surface. Since water can be considered incompressible, the amount of water entering this surface through the tube is the same as the amount flowing out through this surface. And this flow will be the same for all surfaces encompassing the end of the tube. And if the closed surface does not encompass the end of the tube, the water flow through it will obviously be zero. The amount of water flowing into this surface at some parts will be equal to the amount flowing out at other parts. Now let's imagine that we are dealing with a certain section of the surface and want to calculate the water flow through it. How do we do this? The idea is to divide this section into tiny segments. Find the flow through each of these small segments and then sum up all these segments to find the total flow. And when the segments of such a division are sufficiently small, we can consider them flat, with the water velocity being the same across the entire segment. Then the volume of water that flows through such a surface element per unit time will be represented by a parallelepiped like this. Its volume is equal to the product of the base area and the height. Let the velocity form an angle theta with the perpendicular to the surface. Then the height of the parallelepiped is equal to v times the cosine of theta, and the volume of water flowing through this surface element per unit time is equal to v times the cosine of theta. And this quantity is what we call the flux through the given surface element. This formula, v times s times the cosine of theta, closely resembles the formula for the scalar product. But for it to become the formula for the scalar product, both v and s need to be vectors. Well, the velocity ut v is already a vector. The area also needs to become a vector. How is that possible? For this, a vector is introduced that is perpendicular to the surface element and has a magnitude equal to the area of this surface element. And then, for one such element, the flow through it will be equal to the scalar product of v and s. Then we need to sum over all the elements. Let's denote the velocity of each element as vi and its area, the vector-oriented area as si. And then we need to sum all vi and psi over this partition. Well, those who understand will immediately say that since these elements are infinitesimally small, we need to transition from summation to integration. And thus, we have determined what the flow of water through any given surface is equal to. Now we can generalize this formula and say that it is valid as a definition for any vector field. And now, Alexei will apply this definition of flow to the flows of an electric field.
And of course, the electric field doesn't flow anywhere. However, it will be convenient for us to imagine that the electric field flows out of positive charges and into negative ones. And then we will be able to apply the formal mathematical definition of flux to the electric field intensity vector. And we will start with the simplest symmetrical case and consider the flux through a spherical surface at the center of which is a point charge q. In this case, The electric field intensity vector is the same everywhere on the surface of the sphere and is perpendicular to it everywhere. It is directed along the radius, and then the flux can be found by simply multiplying the magnitude of the electric field intensity E by the surface area of the sphere, S. The electric field intensity is equal to kq divided by r squared. And the area of the sphere is 4 pi r squared. R squared cancels out, and we get 4 pkq. Thus, the electric field flux is the same for all concentric spheres surrounding the point charge. And this happens only because the area of the sphere increases proportionally to the square of the radius, while the electric field intensity, according to Coulomb's law, decreases inversely proportional to the square of the radius. Lesha, look, you just said that the flux through all the spheres will be the same, due to Coulomb's law. But what about water? After all, there is no Coulomb's law there. And the flux through all the spheres encompassing the end of the tube is also the same. Of course, the amount of water we supply through the tube will determine the flux. But from this, we can conclude that in larger vessels, the speed of the water will decrease inversely proportional to the square of the distance from the end of the tube. Understood. And it's the same with light. We have a light bulb. It shines in all directions, and therefore the illumination decreases inversely proportional to the square of the distance from the bulb. It turns out that with the electric field, everything is kind of reversed. Yes, and the flux is conserved only due to the validity of Coulomb's law. And probably this will come in handy for us later. Exactly. Now I will prove that the electric field flux will be exactly the same for any closed surface enclosing a point charge. And it doesn't have to be spherical. Let's highlight some small area on the surface and the corresponding cone, with its vertex at the point where the charge is located. The electric field flux through any cross-section of this cone will be the same. Let's denote it as phi. Now let's look at our small area. And let the area vector C with an asterisk form some angle theta with the electric field. We already know that the field flux phi I with an asterisk through this area is equal to EC with an asterisk or cosine theta. But C with an asterisk cosine theta is the area of the cross-section of the cone S at this point. It turns out that the flux through the inclined and through the cross-sections of the cone will be the same. And this will be true for any small area, which means for the total flux created by a point charge as well. And here we have the result. The electric field flux through any closed surface enclosing a point charge does not depend on the shape of this surface and is equal to 4 pkq. This is Gauss's theorem for a point charge. Additionally, it should be noted that in the SI system, the coefficient k is conventionally written as 1 divided by 4 pi epsilon naught, where epsilon naught is the electric constant. And it is written this way, obviously, so that the 4 pi cancels out. And then we have that the flux is equal to q divided by epsilon naught. But what happens if the closed surface does not enclose the point charge? In this case, we will similarly draw cones. And it is evident that for each area where the electric field enters, there is a corresponding area from which the field exits. We already know that the fluxes through these areas are equal in magnitude. However, the sign of the fluxes will be opposite. If the electric field exits the surface, the flux is positive, and if it enters, it is negative. Thus, the total flux through the closed surface will be 0.
And so Alexei has done the main part of the work, and now we need to summarize and ask what happens if we have not one charge, but several? Some are inside the closed surface, some are outside it, some are positive, and some are negative. And since we have the principle of superposition of electric fields, meaning each charge creates its own electric field, this means that each charge creates its own electric field flux through the designated area, doku, da tiokopo, and then all these fluxes are added together. And a mathematician would say at this point that this happens due to the distributive law for the scalar product. And thus we have the result. The total electric field flux through a closed surface is equal to the sum of the charges inside that surface, but again taking into account their signs, divided by epsilon naught. This is Gauss's physical theorem in general form. Now we will look at some consequences of it. And as the first example, we will find the electric field of a uniformly charged sphere outside of this sphere. Well, obviously, due to spherical symmetry, this field will be directed radially everywhere and at equal distances from the sphere, that is, on the spherical surface enclosing this sphere. With the same center, it will be the same everywhere. Well then, we find the flux. It is equal, on one hand, to the magnitude of this field times the area 4 pi r squared. And on the other hand, it is equal to the charge that is inside, that is, the total charge of the sphere divided by epsilon naught. We equate one to the other and see that the field of the sphere exactly matches the field of a point charge of the same magnitude that would be located at the center of this sphere. And now we will do something more interesting and find the electric field inside a uniformly charged spherical shell. Well, for this purpose, we select a spherical surface with the same center inside this layer and state that the electric field flux through this surface is equal to the charge inside this surface, and the charge is 0. Therefore, the flux is also 0. But this flux is again equal to the product of the field and the area, and due to symmetry, the field must be the same everywhere, directed along the radius. And so we find that the electric field on this selected surface is 0. But we could select such surfaces with any radius within the spherical layer, which means the electric field inside such a spherical layer is 0 everywhere. It simply doesn't exist there.
I must note that the results that Andrei talked about were obtained by Newton 150 years before Gauss. Newton, in his theory of gravitation, assumed that material points attract each other according to the inverse square law. But he did not know Gauss's theorem, and he made his calculations directly by considering the forces, acting on a material point from the infinitesimally small elements of spherical bodies. It's as if we continued to use Coulomb's law in our calculations. But it is evident how much more convenient Gauss's theorem is.
And now we return to the wonderful experiment where a charged polyethylene ring hovers above a charged plastic tube. But you can see that I have to move my hand back and forth constantly to keep the ring above the tube. But the question arises, is it possible to create such a system of electric fields so that this ring, or simply any charged body, is held suspended in this system? That is, so that the electric field compensates for the force of gravity, and the position remains stable. If it moves to the side, the body would return to a position of stable equilibrium on its own. And I will consider the simplest case and prove that it is impossible to create such an electric field in which a point charge can be held suspended. Well, indeed, to compensate for the gravitational field, it is necessary to create a uniform, oppositely directed electric field. These fields will cancel each other out. But in such a situation, the equilibrium will still be indifferent. If we push the charge, it will continue to move in the direction we pushed it. And for the equilibrium to be stable, the charge must always return to this point when deviated from the equilibrium point. And for this, an additional electric field needs to be created that will always bring it back. Here, I have drawn it in the vicinity of the charge. Well, now I remove the charge and enclose the place where it was with a closed surface, most simply a spherical one. And I see that there is a flow of the electric field entering inside this surface. But then there must be a negative charge inside. and there is no negative charge there, it's empty. Therefore, it is impossible to create such a field. And it is impossible to ensure the equilibrium from which I began this reasoning. Well, Ershov's theorem states that any configuration of point charges will be unstable if no other forces act on it besides the Coulomb forces of attraction and repulsion. We will discuss other applications of Gauss's theorem in videos about electric fields around conductors and about capacitors. For now, please write your comments and questions under this video. And thank you for your attention.